Yes, here we go.
Okay.
Yeah.
Okay.
Okay.
So, so I just wanted to acknowledge the people involved. Thierry Roudier, who is a colleague of mine in Toulouse, who's been a long-time observer of the solar surface. Michel Riotor, also a local colleague, who put me on this subject when I was a student, actually. Alex Chikoshin in Oxford, who has been involved in a bit of theoretical analysis with me on this problem. And a colleague from Dan, Peter Haynes, who's also been a visiting professor in Toulouse in recent years, who's been involved in some discussion on transport. And Paul Barrer, a student of mine, who worked last year on some of this problem. Okay, so as I told you, the sun is the closest thing we have to study astrophysical fluid dynamics and to study many processes actually in astrophysics, not just fluid dynamics. So this is just a picture taken in UV light. That's a very recent picture from some colleague of yours in the UK, notably. Which shows something very important. And well, first, it's beautiful. Second, from a scientific perspective, it shows something very important. If you, the resolution of this image is such that if you take the pixel or the smallest physical detail that you can see in this image, and the scale of the sun itself, the ratio between these two scales is of the order of 10,000. And of course, this is due to a resolution limit of the instrument. It's not due to a physical process. There's some much bigger scale separation available to physical processes in the sun. But already we have access with high resolution observations today to processes that have a 10,000 ratio in scales. And what you can see is lots of things that are, well, locally homogeneous or statistically homogeneous in the quiet sun, and much more organized patterns like these sunspots and arches that extend to the corona. Some small scale shredded stuff, some large scale organized stuff. And if I give you the equation of MHD in general, or some basic physics equation, and I ask you, what can you get out of these equations? Well, if I ask you to predict what the sun is going to look like just from this equation, what would be your guess? Well, your guess would be very simple, because if you take fluid dynamics equation, the first thing you do is you do hydrostatic equilibrium, and you would find that, you know, there is pressure, there is gravity, and you find that this big ball of gas is going to get into some kind of equilibrium. And then I give you nuclear physics, and you start to say, oh, maybe we can do fusion and all that. Well, but if I can give you all this, can you guess that there are things like sunspots or all these things here that you can see all these details? Probably not. And I found this quote in Feynman, very interesting. And he says, our equation for the sun as a ball of hydrogen gas describes a sun without sunspot, without the rice grain structure of the surface. That's granulation, which I'm going to talk about in a few minutes, without prominences, without coronae. Yet all of these are really in the equation. We just haven't found a way to get them out. So I think in the conclusion to the chapter on fluid dynamics, to explain all the diversity and wealth of information that you get and physics that you get in relatively simple equation, and that don't appear immediately, but which are there, right? And of course, since 1964, before 1964, we already knew that there was, of course, turbulence and lots of nonlinear patterns and all that developing in fluids. But since then, especially in astrophysics, we've made a lot of observational progress, theoretical progress. We have much bigger computers. So the last 50 years we've been able to get more into, well, what's really in the equation. And usually as theoreticians on numeration, what we do is we run the biggest simulation possible with the kind of equations we have, and we look at what's going out. But we never really know if it corresponds to astrophysics, because in general, we are not in the right regimes, we are not asymptotic in any way. And at the same time, we don't have the resolution to observe most astrophysical objects, like accretion disks, or if you look at the intracluster medium of galaxies, you would see fairly well-resolved pictures, but you don't have the time information, the time dependence. If you look at stars, usually, except for a few stars for which we now have interferometry, you just see a point. You don't get to resolve everything. You get a bit of spectral information, but not much space-time resolution. And the only real system for which we have that, and which can help us to make progress with understanding all these hidden dynamics and all this physics, is the sun and all the plasma in the and gas in the solar system. With, of course, there are bits of information available from other systems, but those for which we really can get space-time information somehow are in our solar system. And so the sun is really, in that respect, something very important, and so is, for instance, the solar wind. So I'm going to show you what's going on for what we can see for the sun, and try to convince you why that can be useful. So we have, first of all, on the sun, there is a big diversity of conditions. You have the atmosphere and corona. You have the interior. They have very different densities, temperature, equations of states, degrees of magnetization. If you go up to the solar wind, collisionality, etc., etc. So if we restrict our attention to the solar convection zone, which is a 30% external part of the sun, essentially, you will figure out, in terms of fluid dynamics quantity, that the typical ratio of the magnitude of inertial processes over viscous processes is huge, of the order of 10 to the 10. And that means that's something that's very complicated to model numerically, because it means you need a big separation of scales to describe all the relevant processes. If you do the same for the ratio between magnetic induction and magnetic diffusion, you will find something of the order of 10 to the 6, 10 to the 10, depending at which depths you are looking at. The ratio between viscosity and diffusivity is also very small. That's called the magnetic Prandtl number. That's also a challenge for numerics. And also in terms of rotation, we are in fairly asymptotic regimes, which are hard to describe numerically. So this is a bit of an extreme astrophysical fluid dynamics lab, or fluid dynamics lab. It's not really extreme by the standards of astro, because there are objects in the universe with much more energy, but still, in terms of if you want to have a fluid dynamicist point of view, it's very extreme. And the fact that you have all these conditions, you have MHD, you have lots of things happening with reconnection, convection, all kinds of things. That means you can use this, since we are close to it and we can monitor it fairly well, to study processes like extreme turbulent convection, transport processes, diffusion processes, dynamo processes, of course, magnetic field generation, the effect of rotation on flows, in ways that you cannot do on the Earth. Of course, you cannot stick a probe directly in the sun, but you can observe its surface, at least. And on top of that, you can also do seismology, which gives you quite a lot of information on the internal structure and dynamics. So this is the surface viewed with a ground-based telescope called the La Palma Swedish Solar Telescope, which has tremendous seeing in very stable images, and produce these very, very nice videos or movies of boiling fluid at the surface, hydrogen. So the little cells that you can see here have a typical size of 1,000 kilometers, so that's pretty much the size of France, each of them. That's called granulation, and it's a characteristic of all stars which have a convective envelope. And this is a very thin phenomenon. It's a dynamical phenomenon that develops in the superadiabatic layer just below the surface over just a few hundred kilometers, and corresponding to the overturning of surface convection as radiative cooling takes place. So this is pretty well described by numerical simulation these days. It's been studied for more than 30 years now, and has been very well modeled by people like Bob Stein and Åke Nordlund, for instance. And it gives you an idea of the kind of dynamical wealthiness of information that you can get from the sun. So there is another scale at the surface of the sun, which is less well known than granulation, and it's called supergranulation. So if you look on the image on the right here, what I call the orange skin plot, what it is, it's an image taken using Doppler imaging. It means that you take a spectral line and you measure whether the line is Doppler shifted in the red or in the blue. And so it gives you an information about at different points on the surface whether the fluid is going towards you or away from you. So red is towards you, and red is away from you, and blue is towards you. And you see this kind of granular quote pattern, but this is not the granulation that I showed before. It's a much bigger scale. It's 30 megameters, 30 times larger than granulation. And it's been detected since the 1950s. Granulation was detected much earlier in the 19th century, actually. And nobody, it's been a long time controversy in the solar physics community what it's all about, what's the origin of this, because granulation was recognized as an important dynamical pattern. And so the question was whether this was also some kind of convection, or whether it was due to some kind of inverse cascade of smaller scale granulation dynamics, whether it was associated with rotation, with another physical phenomenon due to stratification or whatever. And because it's the numbers that you need to put in the simulation, the parameters to simulate that, and the scale at which they are such that it's a very difficult phenomenon to model numerically. So as a result, we didn't have for a long time many numerical clues about the dynamic origin of this, and also the fact that observations were limited to say a little square like the one I'm drawing here, which is comparable to this kind of image made with a refractor at the Pic du Midi in our observatory. You didn't get a full view of everything for quite a while, and there was no dynamical view of this phenomenon either. So what I'm going to show you that with new observatories, we can do better than this today, and we've made some progress, I think, in trying to understand this. So the new observations I'm going to talk about are done with the Solar Dynamics Observatory, which is a NASA satellite, which has two main instruments, one called HMI, which does photospheric imaging, so imaging of the surface with a Michelson Doppler imager, so producing precisely the kind of image that you can see here. This precise one was obtained with SDO's predecessor called SOHO. And there is another imager for the atmosphere on corona, and I'm sure you've all seen these very fancy pictures of coronal mass ejection at high resolution done with SDO in the news or elsewhere. So I'm going to focus on HMI today, on the data from HMI. So the great thing with SDO is that, well, it's at a Lagrange point, and it monitors the sun every day. It's been doing that for the last 10 years, every day, 24 hours a day, without almost any interruption. So we have continuous monitoring with all these instruments. And you have, with HMI, you have a camera which has a 16 million pixel, with 16 million pixels, and that corresponds to a resolution at the surface of a little square of 300 kilometers by 300 kilometers. So we can do monitor all the dynamics that's taking place at scales larger than that. And so there are like three main products which I'm using. One is white light intensity. So this is an example of a full disk image. I'll zoom on that later on. This is like a Dopplergram with no removal of any systematics or whatever. It's just, you can see the rotation dipole of the sun with one face coming towards us and the other side coming away. And the last one is the green and yellow thing here. I don't know if you can see the details, but I'll show you in more detail later. These are magnetograms. So you can measure also the magnetic field along the line of sight. And all the three maps I've shown here are for a period of time or precise time where the sun was very quiet. No sunspot, no large-scale magnetic activity. Because what I'm going to be most interested in is the state of homogeneous, statistically homogeneous turbulence in the quiet sun, aside from all the global activities, the 11-year cycle, and all that. So, and the fact that SDO monitors the sun every day for the last 10 years, and the sun has been pretty quiet in that period, allows us to have an extended period where there's nothing except for this statistically homogeneous signal at the surface, which is very good to study these kind of things. And well, one of the good things with SDO, if you don't know and if you're interested in that, it's that all the high resolution data is public, and everybody's welcome to use it because they have lots of it that they don't really know what to do with it. So the quiet photosphere studies, we've used two different observation periods, one in 2010 and a more extended period of 6 days uninterrupted in 2018, which we used to study transport phenomena. So this is an image of white light and again a magnetogram. So this is what you see if you look at the raw white light intensity data in time. I don't see if you can see all the noise on your screens, things moving fast. So the black square is just my screen. The main image that you see, the black square and it tells you which portion of the disk is covered. So if you look at this picture, it's very messy, lots of noise. So you see a bit on the final image, the granules appearing, but as a time process, it's very noisy and messy. And the reason is the acoustic oscillations of the sun, the 5-minute acoustic oscillation pattern, which makes everything vibrate very quickly. So since we have an image every 45 seconds, you kind of sample that, and you can do helioseismology. But if you're interested into the lower frequency dynamics like granulation and all that, you need to filter that out. And I'll show later how you can do that. So this is the Doppler, same idea. The acoustic oscillation gives you little motions at the surface, and that creates all this noisy behavior. And on top of that, you can see the large-scale magnetic dipole, and you can also spot on the global disk the orange skin associated with supergranulation. And this is a zoom on a magnetogram with rotation not removed, where you can see all these small-scale dynamical activity. So typically, if you can identify visually some cells in that in this image, they are typically at the supergranulation scale or slightly smaller, so of the order of 10,000 kilometers to 50,000 kilometers for this kind of stuff. And you see all this evolving dynamics for the small-scale turbulent magnetic field at the surface. And so the question is, of course, well, you see things, it's very beautiful, it has high resolution, but what can you do in terms of learning physical information from all this high-res data? So first of all, when you look at the time and space resolution of this instrument, and if you're interested in the low frequency dynamics of convection, of surface convection, well, everything is well resolved. Granulation is well resolved. The typical overturning time of granulation is 5 minutes on the sun. Supergranulation is more like a day to 2 days. So you can do some time space resolved study of these processes with this instrument. And that was not necessarily the case with previous instruments like SOHO, which didn't have exactly the same sampling. And also the main advantage here compared to ground-based telescope like the La Palma Observatory is that you have global coverage, and so you can study this phenomenon from a global perspective as something that paves the entire sun, and not just like a local study on which you point your local field of view on which you point your telescope. So that's all the advantage of that. So this is the main disk, and this is the first zoom here, which shows you many granules. And if you zoom further, you can see even more granules, which gives you an idea of the breadth of information in this image. So what we do essentially in terms of observational inference here, if you take, we segment all the little granules one by one with some algorithm, of course. So this is a local recipe that was developed over the last 15 years by the observation group in Toulouse. So you apply an algorithm here to segment all the images into small granules, and you track them individually over their lifetime of a few minutes, image after image. And then you take a little patch of them and you average their individual velocities, and you construct some kind of Eulerian velocity field at the surface thanks to the individual Lagrangian trajectories of these granules. And what you hope to do this way is to track the velocity field at the surface, the horizontal velocity field at a scale that is at the scale of your coarse graining. And typically, this gives you a good estimate of this velocity if your coarse graining scale is of the order of 2,000 to 3,000 kilometers. So you use the granules to derive the large-scale Eulerian field. You can test that the technique works with numerical simulations. So that gives you one component of the velocity field, which is the horizontal component. So we call that coherent structure tracking. And from that, you can construct Eulerian velocity field maps of the horizontal velocity field with a resolution of a few thousand kilometers and a typical time scale of 15 to 30 minutes, which is the time you need to average the granule motions. Now, thanks to the Doppler, that's through the light intensity images that you do that, because you segment light intensity images. You can also use the Doppler information to measure the line of sight velocity. That means perpendicular to that plane where you were measuring the horizontal velocities, thanks to the Dopplers. And from there, we have the raw resolution of the instrument, so 350 kilometers and 45 seconds. The problem, as I told you, is that you have the acoustic oscillation. So what you do is you take these images, you take the harmonic transform of them in spherical harmonics and the Fourier transform in time. And what you see is what is called hodochrone or time frequency diagram, if you wish. You can see all these ridges which correspond to the different P modes of the sun with different number of nodes. And then at the bottom, where you have most power, this is the low frequency component, which is a convection. So essentially, if you do a low pass filter on this data and then get back to your regular space and time, you can filter out the oscillations and end up with just the convection signal. So just to summarize, you have the horizontal velocity field at the surface or the in-plane compared to the observer velocity field from the coherent structure tracking, and the out-of-plane component from the Doppler. So then you try to harmonize the data in a way that at the same resolution and all this, and then you make a transform to get essentially in the frame in the spherical coordinate frame of the sun, the radial and meridional and azimuthal component of the velocity field through a transform. So that means you essentially, with this technique, what you can get are the three components of the Eulerian velocity field at the surface. You don't have access to information below the surface, but at least you get three components over the whole surface with a typical resolution, which is this, a few thousand kilometers and a time that's of the order of 15 to 30 minutes. So this is the kind of things that you see if you try to retrace that. So the arrows are the horizontal part of the velocity field and the colors are the vertical part. And what you see typically on this in this pattern is supergranulation with converging and diverging cells of fluid, which are more or less correlated with outflows and downflows. And I'll come back to the fact that the correlation is not always great. This is due to the fact that actually the vertical velocity field is much smaller than the horizontal one by a factor at least 10. So this is a local velocity field snapshot of, you see 10 degrees latitude and 10 degrees longitude centered on the center of the sun, on the equator, sorry. And from that, so this is a global map, and the little square is the previous field of view which I showed you. So you can get that at every time for the full sun. And if I come back to my original pitch, there are not that many systems for which you can get this kind of dynamical information in astrophysics, right? So this on the left, what you have here are color maps of the divergences of the field. So how the flow just expands at the surface or sinks. And on the right, this is a visualization using line integral convolution, which gives you an idea of the Lagrangian trajectories of, if you were to put tracers at the surface, overlapped with the divergences. So you can, this is for the spheroidal component, so the cellular component of the flow in terms, for those of you familiar maybe with the CMB, this is a bit like decomposition into E and B modes for the polarization of the CMB. We can do the same for the vector of the velocity field. So this is more like the quote electric field representation for the part of the velocity fields as divergent. And then the other one is like the B modes for the CMB. This is like the torsional part of the spectrum, if you want, or the vertical part of the spectrum. So here the blue and red are like the little vortices that you can reconstruct from this decomposition. And this component, the toroidal component, is actually also much smaller than the divergent one. So the dominant part of the flow is a cellular flow with large-scale divergences and convergences in the blue lines here. So this is smaller. So overall, if you try to play the games that people in turbulence usually play, or when you do MHD simulation or hydro simulations, you take an energy spectrum of your flow to see what your flow characteristics are. So this is what you get in this case. So the blue line here, so vertical is spectral energy density, and horizontal is angular degree in terms of spherical harmonics decomposition of the flow over the full surface of the sun, which we can do because we have a global observation here. What you see in the blue line is the spectrum, the kinetic energy spectrum for the spheroidal component, so the divergence-like motion, the cells. And you can see there is a clear peak at a scale of L equal 120 here, which corresponds to supergranulation. The toroidal component, or the vertical component, is much smaller, as you can see, and it's much flatter too. The black one is radial velocity. And as I told you before, you see it's very, very small compared to the spheroidal horizontal part of the flow. And the red one is what you would get if you just take the spectrum of the Doppler signal, which is actually a mix of the horizontal and vertical component because of projection effects on the surface. So this is the main quantitative results that we can get with this observation. This is the spectrum. And what this spectrum tells us first is that there is clearly a peak of injection of energy, what you would traditionally associate with the injection scale in a turbulent flow at the scale of supergranulation. And this was not very clear with the previous observation like those done with SOHO, because depending on how people used to analyze these curves, the Doppler signal, because people could not decompose between the horizontal velocity field and the vertical. And so if you just look at the Doppler, you see that it's much harder to see a peak here, especially if you zoom at in the central region where the horizontal component of the flow is almost perpendicular to the line of sight. You don't catch a lot of this signal in the Doppler. So there was always a bit of controversy of whether this scale, supergranulation, was actually a very energetic scale or not. And with this observation, we can say without ambiguity that yes, the horizontal flow is definitely the peak injection scale of the turbulence at the photosphere. The other thing that's important is that usually if you look at a spectrum for isotropic homogeneous turbulence, the standard Kolmogorov turbulence, well, it's isotropic. So if you take the spectrum of one component, say horizontal, or another component, vertical, or in any possible direction, and you will get the same energy spectrum for all the components. And here, that's not what you see. Here, the horizontal spheroidal component has much more energy than the vertical one. So this is not your isotropic homogeneous turbulence at all. This is strongly anisotropic, a strongly anisotropic flow dominated by cellular motion, like motion that you see from the face when you look at the sun. So this looks like very anisotropic thermal convection driven at supergranulation scale. So this is just a summary of this. And the question is, yes, these are observational facts. It's anisotropic, it's driven at supergranulation scale mostly. And the horizontal flow is much, and it's mostly cellular. So it looks like convection. One point here is that the cutoff in the energy here is due to the algorithmic procedure that we have to use to compute the horizontal flow, because I told you we need to average to coarse grains everything at 2,500 kilometers. So this is not the cutoff in the actual dynamics at the surface of the sun. Everything continues below, right? It's just that we cannot catch that with our observational techniques. So, but if you look at, so here I've downgraded the Doppler to have the same resolution as the horizontal velocity field. But if you just take the Doppler alone, you would see that actually there is an increase of the radial velocity as you go to smaller scale down to granulation. And in terms of radial velocity, the peak takes place at the granulation scale, around 1,000 kilometers. So you have these two spectra here, the horizontal velocity spectra and the vertical velocity spectra, which actually cross at some intermediate scale where things become isotropic. And that scale is roughly the size actually of granulation, which sits around here in terms of scale. But at these scales, at the scales that we can look at from a dynamical perspective with all the three components, the flow is strongly anisotropic. That's the idea. So the question is what, now I'm putting my theoretician's hat and I'm trying to make a physical and theoretical sense of that. Can I describe that through a nice formal phenomenology or not? I already told you there is no such thing as a Kolmogorov turbulence at the scale we look at. So we need to be a bit creative with this. So just to get a better intuition for that, I'm going to revisit some of the simulation I did many years ago, which are large aspect ratio simulations of turbulent convection in a large aspect ratio domain. What this means is that, so I'm essentially simulating Rayleigh-Bénard convection here, convection between a hot and a cold plate, except that it's stratified in density. But the specificity of the simulation you are seeing here is that the dimension of the simulations, which is a vertical, where gravity is, the out of plane direction here, the size of the domain is just 1. Okay, if you call that 1, then the horizontal dimension that you see here is 40. So it's a very wide simulation compared to the thickness of the convection layer. The point is we were interested in this large-scale dynamics, and we wanted to see if some large-scale pattern emerged in this old simulation from 2004. So at the time, these were very costly simulations. This was, I think, 1,000 squared with spectral resolution and 100 points in the perpendicular direction with compact finite difference. So something like 1 million CPU hours, if I remember well, in 2004. And what you could see in this simulation, I'm going to play it again. You start with a fairly small scale pattern, which is the most unstable linear convection scale in your problem. And as time goes and the nonlinearity develops and the simulation saturates, the most energetic scale shifts toward larger scale. And at the end, you will see a much larger scale dominant energetic pattern, which you can spot here in terms of these temperature rings here. So this is translated on the right by the spectra for the temperature and kinetic energy. First, you see in the early times of the simulation, you see a peak at horizontal wave number of order 60, which corresponds roughly to the vertical size of the box. And as the simulation is going to progress, you are going to see a shift of the peak toward larger scale and some turbulent cascade developing. So I'll play it again. So this is a smaller scale originally, the most unstable scale. And as time goes, over many turnover times, you start to see the larger scale dynamical pattern emerge. So when we found that in 2004, we were, of course, a bit enthusiastic. This was the first simulation of this kind. At the same time, there was another one done by a fluid dynamics group. But the problem we had is that if you look at the surface, so you see the smaller scale pattern in the close to the surface, which correspond to what we would call granulation at the surface. You can identify that with the superadiabatic layer. And then on top of that, you see this larger scale pattern, which of course you would like to say is reminiscent from supergranulation. But in practice, in the simulation, essentially, if this is 1, well, the size of the bigger rings was 8. So this was not the aspect ratio, the scale ratio of supergranulation to granulation. So we call that mesoscales because it didn't really look like supergranulation. So in recent years, I've come to revisit this interpretation of this simulation because there have been many more simulations by other groups, which now shows that all of them show that there is like this dual scale thing going on with some nonlinear organization of the flow at larger scale. But some people have found through parametric study, which I wasn't able to do because of the cost of the simulation at the time, that the actual scale ratio between these two scales depends on things such as stratification, the amount of density ratio between the surface and the bottom, or the depth of the entropy jump or superadiabatic layer at the surface. So for instance, this is a series of simulation by Cosset and Rast from a few years ago, where they played the game of patching an almost isentropic convection zone with different superadiabatic layers in a way that is continuous and differentiable, I think. And what you see is that the peak scale of the spectrum depends on the width of this superadiabatic layer very much. So essentially, what this global large scale is dependent on how hard you drive the system. And if you have let's say 100 points available in the vertical, you cannot drive your system very hard. So if you are in a position with better numerical resolution to drive it harder, well, you would see that this peak would shift. And the question is at which point you become asymptotic. So to come back to this simulation, what I think today is that this was just a manifestation of something which is supergranulation in reality in our simulation, except that we are not driving asymptotically, and we are not in all the right parameters regime in terms of thermal Prandtl number, Rayleigh number, stratification, density ratio, etc. But at least you get a signature of nonlinear organization or nonlinear dynamics in this simulation. So the interesting point about that then is that if you look at the dynamical analysis of that simulation, which is here, you can try to play the scale-by-scale energy budget game and try to see for each horizontal scale that you see in this, that you can decompose through like a Fourier analysis, where the energy comes from and where it goes. So, and what you see here is that at large horizontal wave scales, so small wave numbers, if you take this equation for thermal convection for the kinetic energy, in a statistically steady state, the kinetic energy in each mode is constant. So this d over dt of energy is 0. And you end up with three terms. This transfer term, which is just inertial term, v dot grad v, the effect of the turbulent cascade, if you like. F of k here is the buoyancy term, the forcing associated with the effect of buoyancy. And D is dissipation. So at large scale, you essentially find that the big scales that you see are driven in the nonlinear regime by buoyancy. And then inertia, the turbulent cascade, cascades down this energy to small scale where it is essentially dissipated. And this is an important analysis. It looks like a standard turbulence thing. You get an injection scale, transfer to small scales, and dissipation at small scales. This is essentially how it goes. But in the context of supergranulation, it's important because there were some theories before this simulation which suggested or speculation, which said that maybe you could get an inverse cascade. That means you take energy at small scale through some forcing process, and then through transfer, you inject energy at large scale. And this is actually the opposite that's going on. So this kind of kills the idea of an inverse cascade in that problem. What you see instead is that there is a dominant equilibrium at large scale between buoyancy forces and inertial forces, which extends to actually a fairly broad band range of scales. So the injection range is pretty broad, and you need to pay attention to buoyancy in a fairly large broad band of scale. The other information on this plot is that you take this red point here, this scale. This is the most unstable linear scale in the system. So this is what your dispersion relation would give you, right? If you make analytic theory for the thermal convection in this system, or semi-analytic because you need to solve things numerically because of stratification, you will find that if you put your system in an unstable situation, it will grow at this scale preferentially first. That's what you saw on the previous animation. And the key point to observe here is that the final state has nothing to do with this scale, right? So all your linear, quasi-linear predictions that you can make based on, that people usually do based on linear theory, well, in practice, they don't apply to what you see in simulations. There is a high degree of nonlinear organization in the flow, which makes the energetically dominant scale in the end very different from what you could say from linear theory. And I think that's an important point to make in the context of astrophysical fluid dynamics in general, where lots of calculation of transport are based on quasi-linear theory, for instance. So what we can say from that is that you can try to make some turbulence phenomenology based on this observation. And for that, I'm going to get back into more of a classical approach to turbulence, where we use structure functions to try to derive scaling phenomenology, scaling laws for different quantities involved in the problem. So you look at the dynamical equation for the fluctuation. So you have this is essentially a Rayleigh-Bénard, if you like, which you can adapt to the case where there is density stratification. And you want to derive evolution law or scaling laws for the statistic of fluctuation increments. So for instance, for temperature, I can take the temperature at a point x plus some correlation vector minus temperature at some point x, and take the powers of the moments of this distribution for the observations or the simulations, and try to see if there are some scaling laws, right? So this is, for instance, what Chris has been doing quite a lot for solar wind turbulence or other dynamical phenomena in space physics. So you can do that for convection, for instance. And so the typical approach to that is you derive exact law, which are called Kolmogorov and Yaglom relations. So the Kolmogorov law is essentially the law for the third order velocity moments or increments. So if you remove this term, you recognize Kolmogorov's 4/5 law, which tells you that the fluctuation increments go like r to the 1/3, the separation between the 2 points where you make the measurements, and that gives you the k to the -5/3 spectrum. But here we have another term which is important, which is a buoyancy forcing term, and I'm going to keep it here. There is another equation for the passive scalar, the temperature, that you can work, which provides you with a scaling law for the mixed third order correlation function for the temperature and the radial velocity. And that's called Yaglom's law. It's the equivalent of the 4/5 law for the temperature for the passive scalar. It's called the 4/3 law because it has a 4/3 in front here. And on top of that, if you don't have a passive scalar, but if you're in the case where there is a stratification, so it can be stably stratified or unstably stratified, you get an extra term here that comes in this equation. So the important point here, I don't want to get into all the nitty-gritty of this derivation, but it's important to realize that you can get different regimes from just this equation. You look for dominant balances between different terms to look at an interesting dynamical regime. As I told you, if you ignore the buoyancy force in the momentum equation, well, you end up with this relation. Delta U goes like r to the 1/3, and you remove the stratification here, and the corresponding scaling for the scalar is the same. So you end up with k to the -5/3 for the energy and k to the -5/3 for the scalar. But there is a different thing that you can do, and this different thing is, let's say you balance buoyancy with inertia. Right, and this is justified in what I'm looking at by the fact that, as I showed you here, there is such a range of scale where buoyancy is essentially balanced by the transfer term in this, for instance, in my simulations. So if you try to play this game in that case, you balance this with this, you mix a correlation function, you keep this relation between delta theta square and delta U and this term here, for the simple reason that for the most part, when you are in a highly convective state, this is essentially 0 because the stratification is adiabatic. So this is called the constant thermal flux hypothesis, but then you take the different dominant balance in the momentum equation, and if you do that and assume isotropy, that means the radial velocity and along the correlation vector and along the gravity is the same, you end up with simple different scaling relations, which are called the Bolzano-Obukhov relations, which were initially developed in the context of atmospheric science. from which you will get k to the minus 11/5 for the velocity spectrum and k to the minus 7/6 for temperature. So if you look at my spectra, for instance, in the simulation, k to the minus 11/5 is way too steep. So although you would like to think that this dominant balance between these two terms is relevant, it doesn't seem to work. And I was puzzled with this for many years until I got these observational results, which shouted the answer in front of me. And the answer is, this thing is not isotropic at all. So when you make the isotropy assumption to derive the Bolzano-Bukov scaling, this is incorrect. So you need to correct for that, and that means you need to pay attention to the different directions in your system. And the way you do that is you modify the theory. So you keep the constant thermal flux of fluctuation, this assumption I was doing before for the temperature equation. And then you take into account mass conservation by making the difference between the horizontal motion and the vertical motion, assuming that the vertical motion has a typical scale height decided by not by the dynamics, but by the density scale height of your system. And so the only scale that's on which you want to test some dependent is the horizontal scale. Then you have this extra relation now, and then you can modify the dominant balance between inertia and buoyancy to take into effect the redistribution of the pressure when you are anisotropic. This gives you a prefactor in this dominant balance, which is also a prefactor that you get, for instance, if you derive the dispersion relation for gravity waves in the anisotropic asymptotic case. So if you modify your scaling relation like this, your dominant balances, well, everything changes. You get different spectra for the vertical velocity, the horizontal velocity, and the temperature. And the final result is that your vertical spectra goes like horizontal k to the 3/5, so it's growing with k. The horizontal spectra goes like minus 7/5, so much less steep than the minus 11/5 of Bolzano. And the temperature is a bit steeper than before. So this is interesting because now it tells you that you have a growing kinetic energy spectrum for the vertical component and a decreasing spectrum for the horizontal component. And this is precisely what we see in the observations. So this is a comparison now. So the dashed line here is minus 7/5. I've put a minus 5/3 for reference, which is also acceptable in terms of just scaling, but I'll come back to why I don't think it's relevant here. And on top of the black curve here, which is radial velocity, I've put k to the 3/5, which is an anisotropic scaling I predict, and k to the 1/3, which would be just a very quick and dirty modification of Kolmogorov for the radial velocity. So you see, it's not too bad in the sense that it doesn't give completely wrong answer. At least it predicts that one of them is decaying and the other is growing. And the other reason why I don't think Kolmogorov, a modified anisotropic Kolmogorov would be relevant here, although it doesn't seem to do too bad either, is because in terms of phenomenology of cellular flow and all that, it doesn't seem to fit any of the pictures you see from the observations, right? It doesn't seem to fit the phenomenology of a balance between buoyancy and transfer in the simulation. It doesn't fit the fact that the flow is cellular. Kolmogorov is more like rotational flow, and here that's not the case. So in terms of physical understanding and physically motivated phenomenology, this new scaling regime seems to be much more relevant to me. And there is one last point on that. These are observations from my colleague Thierry Roudier, which date back from a few years ago, where he actually spotted through a careful analysis of patterns at the surface that there is some kind of self-similar fragmenting dynamics of the flow at the surface of the convection cells, which seems to be very well understandable in terms of the phenomenology I just described. Namely, what this assumption tells you here is that essentially you cascade and you break down thermal fluctuation into smaller scale thermal fluctuation as the flow goes on. And in turn, so that gives you a distribution over scale of temperature fluctuation, which can give you a distribution over scale of buoyancy forcing through this term. So you have this kind of nonlinear, organized, self-similar regime where buoyancy plays with inertial physics and with the turbulent cascade. So this is just the main interpretation of all this joint observational and numerical analysis. I think I'm going to have to stop here in terms of, yes. I wanted to talk a bit about turbulent transport and diffusion, but I won't have time for that today, so I'm going to stick to the main part on, sorry, I'll skip that. I'm going to skip to the, I just want you to retain the main part of the hydrodynamic part of the talk. So the main thing I want to outline is that because we are looking at the sun and it's very close, we are able to get a very, very detailed dynamical characterization of some kind of strongly driven astrophysical fluid turbulence, some things that you don't have access for things like, say, accretion disks or galaxies or any other stars. And through a determination of the velocity field and high resolution time and space observation, followed over many times and in an ideal environment where all the sun is very quiet, well, we came to some, I think, relatively interesting conclusion for what your typical strongly driven astrophysical fluid turbulence looks like. Well, first of all, there are all the implications for the solar convection problem itself in terms of better understanding what drives supergranulation. The motivation for the development of new turbulence phenomenology that comes from solar observation, which gives you indication about more fundamental phenomenology. I think that's interesting to have things going that way and not the other way around. And in terms of the broader implication, well, when you look at the global scale of a system with lots of strongly driven dynamics, first of all, I think it's now seems to me obvious that there is going to be a lot of anisotropy. I mean, if you look at a disk or even a star, it's on large scale, it's kind of obvious. But in terms of our toolbox for describing turbulence from an analytical perspective, well, we don't have much to. We still don't have much to do that. So. And that's relevant in this context. So we need to make progress with this kind of description of anisotropic physics. And the second important point is, as I showed on the numerical analysis of the simulation, is that you have to be very careful in these strongly driven regimes that actually is what the system looks like in the end, in the dynamically saturated set, has nothing to do with the linear physics. You get strong nonlinear self-organization. This is a domain of nonlinear dynamics and astrophysical fluid dynamics that's barely starting to get probed by numerical simulation. We find, start to find large-scale organization in magnetic cycles, in accretion disk dynamics, this kind of stuff. But here we have an observational clue of this, and which I think shows us by its ubiquity and the fact that you cannot miss it. That this is something that is going to be of general relevance in astro. And we are going to need, I think, many, many more years of numerical simulation and progress with simulation to get into the really understanding how you can describe that in a proper way from a dynamical point of view, for instance, in terms of mean field modeling or large-scale, large eddy simulations, this kind of stuff, because we don't yet understand all the detail of questions like what is turbulent viscosity like in a system like that, what is turbulent diffusion like, what does turbulent diffusion look like, what is its magnitude, is it comparable to viscous turbulent viscosities, etc., etc. We've barely touched the surface of that so far in terms of because the simulations are far from being asymptotic in that respect. So I think this kind of studies, although it has its own limits due to what you can do with observations in general, and maybe I haven't spotted everything, at least it gives you a strong hint that all these phenomena are highly relevant from a broader point of view in astrophysical fluid dynamics. And to come back to the Feynman quote, well, this is something that's not easy to predict from the equations themselves. You have to work hard just to get into these kind of regimes and figure out what it is that the turbulence actually does and how it organizes. So I'll leave you with this, and I can take a few questions if you have some. Thank you.
All right, thank you very much, Francois. So I'm sure there are questions. So, so David is asking a question in the chat. Why is there such a big difference in tau for granulation 5 minutes and supergranulation 48 hours? Is that because of different characteristic speeds?
Yes. So, well, first of all, the horizontal scale is very different, right? So let me come back to this plot. So on the left, you have a lot of little granules. On the right, you have the supergranules. So if you just take the typical velocities that you can measure from these Dopplers in granule, you find something like 400 meters per second. So, and the distance, corresponding distance is 30 megameters. So that will give you at least a turnover time of 5-8 hours, something like that. And then the structure survives for quite a while, typically 1 to 2 days. So for granules, it's a much more violent thing that takes place on a much smaller horizontal scale with a typical velocity of 1 kilometer per second. And so the turnover time is very quick. So the interesting question, of course, is why is there such a well, it looks like these two scales, when I look at this, they are quantified, right? There is a big gap between the two. So what the observations show is that there is actually not a big gap between the two. There is a continuum. Let me come back to the spectrum. Computer struggles a bit. Yes. So this is supergranulation scale. So granulation is here, but as I told you, if I didn't have a cutoff from my algorithmic reduction, then the radial velocity field would go up like that. And at some point around here or here, there is a crossover where things become isotropic. So in between these two things, there is a continuum of scale. What differentiates mostly between the two is that this thing here around granulation is almost isotropic. In the sense that you have all the three components of the flow which are similar, so it looks one way. And when you look at supergranulation, well, it's essentially a horizontal cellular flow because things are so anisotropic at this case, you get big pancakes. So the visual appearance of the two structures is very different. And it tricks a bit the eye into thinking that you have such different scales. Of course, also, this scale is a peak, and our eye is very good at detecting peaks or borders or things like that when we see them. But in reality, what you see is that there is a complete continuum of scale on dynamics between the two, and it is precisely this quote self-similar regime that our phenomenological theory tries to describe. And that means essentially that buoyancy is active over all this range of scale going down to granulation from 1 megameter to 30 megameters. What really singles out supergranulation is that this is the maximal scale at which this thing takes place. So, and I need to complement this answer by saying that we don't yet understand. For instance, I cannot give you a formula to say, well, the peak is going to be at this precise scale. We don't yet have found a way to describe this peak, which would be very interesting for many reasons. But we don't yet fully comprehend how to do that. And the reason is because we need for that to understand essentially, to answer the question, what is the turbulent viscosity associated with all these intermediate dynamics? Can we predict that based on solar luminosity, thermal Prandtl number, stratification of the solar convection zone? These are all the parameters that are relevant in this context, and we need to come up with a physical formula for this that is motivated by physics, and nobody has been able to do that so far. So the results I'm showing here give you an idea that there is a peak, that things are anisotropic, and that we kind of understand that there is a dynamics here that is not Kolmogorov type, but we still don't know for sure what sets the scale of this precise peak. Does this answer the question? No?
And so do results change during the solar cycle?
That's a good question. As far as we know, no.
Right, I'm reading out David's Florian's question. So.
Yeah. So as far as we know, there is no strong detectable trend with this. People have been trying for a very long time to look at dependence of supergranulation with the solar cycle. The problem, of course, was because the cycle is so long. You had one data point from one thing in 1980, and then another one in 1985 from a different instrument, and then another one 5 years later for yet another instrument. So calibrations were different. Nobody was measuring things the same way, not with the same field of view. So comparison was very difficult. And the best that you could get for a long time was just noise, no significant results. So with SDO, as I said, now there are 10 years of data collected, and Thierry, my colleague Thierry Roudier, is trying to figure this out in more detail. So as far as supergranulation is concerned, there doesn't seem to be any significant dependence on any of this. And this is not hugely surprising in the sense that if you look at the energetics of this, for instance, the kinetic energy in this flow is typically much larger than the typical small-scale fields that I showed you in the magnetogram initially. So they are not very much affected by magnetic fields. They more or less advect the small-scale field like if they were passive. And then global fields like sunspots are more like localized coherent structure, but they don't really affect what's going on generally in the quiet sun to a high level. So I'm not particularly surprised by that. It's possible there is a weak dependence, but if it is here, it's small. In terms of granulation, you can also play this game with SDO. For instance, you can calculate how many granules you have on the surface at different times in the cycle using the segmentation I told you before. And here, surprisingly, there is a bit of a difference that's coming, which starts to come in. So I don't think that Thierry has published that so far, but I'm aware that he's working on this kind of problem. And it seems to be a bit of a difference on the size, the typical size of the or number of granules that you can see on the visible disk of the sun on the solar cycle, which I think is kind of interesting. I'm not sure we understand exactly why that would be the case. So he's trying to remove all the possible systematics, which is not particularly easy as usual with systematics.
All right, so any other questions? Chris, do you have a?
Yeah, I have a question. So this is, really nice work, I think. So your model predicts the scaling for the different components, the transverse and the radial.
Yes.
But I'm wondering if it says anything about what the relative amplitudes is. So is it the idea that at the granule scale, things are kind of isotropic because there's no preferential direction there, and then as you go to the larger scales, the reason that the supergranules are mainly transverse is just because of the different scalings?
Yeah, so this is a slide which I didn't have much time to show you because I wanted to concentrate on the buoyancy regime, but I have actually a slide to explain this. Let me show you. So I told you there are two possible dominant balances here. One is Kolmogorov here, and the other one is Bolgiano, isotropic or anisotropic in the first place. So if you try to figure out what is the scale at which all three terms are equal, that means that the transition scale between these two regimes, it's called the Bolgiano scale. You can express it here in terms of the dissipation rate for velocity, thermal fluctuation, gravity, the density, entropy gradient, and in non-dimensional terms, in terms of the non-dimensional transport, the Nusselt number, Rayleigh number, and Prandtl number. So in principle, you get a Bolgiano-like scaling where the dominant balance is buoyancy and inertial terms for scales larger than that, right? And Kolmogorov for scales smaller than this, right? So if you compute that for the sun, it's typically similar to the density scale height, and that means 2,000 to 5,000 kilometers. So granulation itself is pretty much the separation scale between these two regimes. So you would expect that at scale above granulation, you would get a buoyancy-dominated regime, which turns out to be anisotropic, not the original Bolgiano thing, but that doesn't change this estimate because things precisely become isotropic at this scale. And below that scale, below granulation, you would expect that the effect of buoyancy would become subdominant, and then you get a regular inertial cascade, which is fed by what's going on at larger scale through these different regimes. I don't know, does this answer your question, or do I need to get into more specifics on this?
No, that's good. Yeah, that's good.
Yeah. So the point is, this scale is not only the separation between Kolmogorov and Bolgiano, it's also, if you look at things, what separates between isotropy and anisotropy. Because here this term is isotropic in terms of the correlation vector, it just depends on the magnitude. But here you start to see that you have z, which is the gravity direction, but here you have r, which is the direction along your, sorry, the distance along your correlation vector. So you break the isotropic symmetry through this term here, of course, due to the buoyancy, which has a special direction. So this Bolgiano scale is also not only a scale where the dominant dynamical balance change, but also a separation between isotropy and anisotropy.
I see. And just maybe sort of a more general quick question. So what are the, are there any implications for the dynamo theory in this? Because typically the supergranules, people stick with the dynamo somehow, right?
Right. So that's a very good question. So which this is the other part of my talk. I'm going to just show you one picture. So once you have all these flows and you kind of understand their dynamics, one of the key things that you'd like to understand is how do they contribute to turbulent diffusion of magnetic field at the surface? Because as in the context of your question, turbulent magnetic diffusion is a key quote parameter or quantity or process in terms of global magnetic activity cycle. So we started to look at this last year with a student and with Peter Heinz as to how these flows that we derived observationally transport magnetic fields, or at least passive scalars. So we've made a bit of progress on that. One neat result is you can try to, by advecting grids of tracers, to compute finite time Lyapunov exponents for this flow. And this is the kind of things you get. So this is like, I think, a nice, although it has maybe limited scientific value, it's in terms of aesthetics, it's very nice. It's a global maps of finite time Lyapunov exponent at the surface of the sun. So it shows you that you have, so when you do that, you take the maxima of this Lyapunov exponent and you compute what people call Lagrangian coherent structures. And you find these sites where essentially the tracers accumulate or from which they diverge, depending on whether you integrate backwards or forward in time. And these sites are like transport barriers. So for instance, if you imagine you take a small scale magnetic field in the middle initially, it will be advected by the flow of supergranulation, and it will get stuck after a few hours at the periphery of supergranule where the fluid sinks and not get transported further. So that, in that sense, it's a transport barrier. But these structures themselves just live for 24 to 48 hours. So if you're interested into the transport on a longer time scale, which is of course what you want to do for if you look at if you're interested in the transport or the turbulent diffusion associated with that's relevant to the global activity cycle, you need to have observations that give you that can allow you to do that for longer than 1 or 2 days, which is why we try to do 6 days. Beyond that, it's very difficult because the sun rotates, so we lose the local region ends up going on the limb, and then we don't our algorithm cannot work very well, which is why here I've limited things here. So, but still, you can play this game of advecting passive tracers and trying to measure diffusion coefficient. And doing some kind of qualitative analysis like that. And well, what you do if you do this, you find a typical diffusion coefficient. So first of all, what we found a bit surprisingly is that things are not diffusive, even on fairly longer, on time scale longer than the typical correlation time of the flow. They are still a bit highly super diffusive. I don't know if this is going to persist, but that's quite a robust result. But if you try to extract some kind of mean turbulent diffusion coefficient from that, yes, you would find this kind of quantity, 5 to 10 to the 7 square meter per second. And if you compare that to what people use, for instance, for mean field modeling of the solar dynamo for the same parameter, I mean, horizontal transport of a magnetic field, well, you would find that, for instance, this is some kind of coefficient like that extracted from a global solar dynamo simulation. They are in the right ballpark for their mean coefficient or mean transport at the surface. Same, this is also a profile for the turbulent diffusion parameter used in a mean field study from Matthias Rampel from Boulder. And this is my observational results. So I would say that the observation can play a role in constraining this kind of effective coefficients that people want to use to make some modeling of the solar dynamo cycle, and it can also tell you whether or not the global simulations, 3D simulations, are in the right ballpark or not. But this is still a bit of work in progress, but we are working on that.
Thanks, very interesting.
All right, any other questions?
I just have a quick question.
Go ahead.
Can you go to your slide with the isotropy and homogeneous laws?
Yeah.
Written.
Let me.
I just wanted to understand where your arguments come from for the scaling laws, right? Because right before you write these equations up here, you just have a divergence of the, you know, you have a divergence on of the third order moment on the left-hand side.
Correct, yeah.
So here, you're just, you know, you can make an axisymmetric assumption, work in cylindrical coordinates, and then you have just two classes of solutions, some that are concave and convex.
Yeah.
Okay, so you can measure the concavity or convexity of the correlation function to understand which class is correct, and then that will help you narrow down your scaling laws, if I'm correct.
Yeah.
Okay, so this is that's the where the anisotropic scaling law comes from in your next slide.
Well, I try to simplify things a bit here. I mean, these equations here, right? They are the isotropic version of all these equations, right? So I'm using this equation to discuss two classical results, which are the Kolmogorov results and the Bolzano results, when you have this active scalar here, or temperature scalar. So this equation is not generally valid when you are anisotropic and inhomogeneous. Okay, I wouldn't use that form actually. When you do that, I actually have an old paper from 2006 JFM where I did the whole decomposition of this equation in the case where things are anisotropic and not homogeneous, as people have done also with shear flows and other flows like that. So I'm just showing this one for illustrative purposes. What the phenomenology that I describe later in the anisotropic case really relies on is just twiddle algebra based on dominant balances using the relevant polarization of the different components in the equations. But I mean, essentially, you don't invent new term when things become anisotropic or whatever. It's just that there are some fine modification, but you still have a dissipation term like that, and you still have a forcing term like that. So essentially, what we are trying to do here is just to cut through all the technical complexity of this decomposition and try to get to the essential dominant balances by balancing the right quantities together. So this is just a very phenomenological version of applying Yaglom and Kolmogorov theory in this context. So I'm not actually using these two equations to derive these scalings here. This is what I'm doing is at a much cruder level than going exactly through the exact laws. Does this answer the question?
Yes.
Yeah, I would like to say too. I mean, this is I'm trying to do a bit to be a bit of a salesman here because I'm very excited with the fact that I've solved my some of my own questions which I had for so many years, but I don't have a guarantee that this is okay, right? I think this makes sense physically. I think this is there's some consistency with observation. It makes sense in the context of the analysis of the numerical simulation I showed you. But nobody has checked that so far with simulation, and I can't do that with my old simulation because I don't have the data anymore. So I would have to redo them, and unfortunately, I didn't find the time to do that so far. These are just predictions or a tentative phenomenology, which I would like to be studied further by people who are doing simulations of this problem these days. Further, there is no guarantee that this is correct. I just think there is an overall consistency of what we between every element that we have so far for this to be at least relevant in terms of physics.
All right. Any other questions? I think not. So I'll thank Francois again for a very interesting seminar. Thanks for joining us on this first online event. And I think we can conclude the official part here.
I'll try to come to London at some stage.
Yes,
I'll give a seminar on mirror modes for Chris.
We'll start that process as soon as this one is finished. All right, well, thanks everyone for coming. And next week we have another one. I'll announce it as soon as the speaker sends me a title, and then we'll